Students will discuss about the numericals one by one. We'll take around 20 questions. So numerical number 1. Numericals on magnetic effect of current. Suppose the question number 1. Suppose there is a conductor which is infinitely long, carries a current of 5 ampere, and I want to find the magnetic field at a distance of say 10 centimeter from the conductor. Suppose this is a point which is 10 centimeter. What is the magnetic induction? So this is a question and we have to solve it. So the question is to find the magnetic induction. So B stands for magnetic induction. So now the formula for magnetic induction due to straight conductor carrying current I at a distance x is given by this side will be cross, this side will dot, this side it will be cross. The magnetic field will point out of this space and go into the page this side. Magnetic field is mu 0 upon 4 pi 2I divided by x. This is the formula. So therefore we know that this value mu naught upon 4 pi is 10 raised to minus 7. So this is 2 times 10 raised to minus 7 into I, that is 5 ampere, divided by the distance, that is 10 centimeter. The distance is in 10 centimeter, you have to convert it into SI system. So this 10 centimeter becomes 10 into 10 raised to minus 2 meter. Putting this value here, this is 10 raised to minus 1. This goes up 10 raised to plus 1. So the answer is, here is 1 5 to the 10, here is also 110, 100 will be minus, so it is 10 raised to minus 5 Tesla. This is the unit, SI unit of magnetic induction. So 10 raised to minus 5 Tesla, or Weber per meter square, whatever you say, or Weber per meter square. This is the answer to this question. Okay, so let us take one more question. I'll write the question for you. A current of root 2 ampere is flowing from south to north in a straight conductor. South, north. 2 ampere current is root 2 ampere current is flowing in a straight conductor wire. Find the magnetic field due to a 1 mm piece of wire. Due to a 1 mm piece of wire at a point 10 centimeter northeast from piece of wire. So write the question for you. Now you have to find the, so this is a conductor which is pointing south north, and this is the current that is flowing. We have to find the magnetic field northeast. Suppose this is east, this is west, this is north, and this is south. Your question is to in northeast direction. Northeast is 45 degree. So this is 45 northeast. So therefore, and this distance is 10 centimeters from the piece of. So this length is suppose this length. This length is suppose this length is suppose 10 1 mm. This length is 1 mm. So I'll put it here 1 mm. Okay. So you have to find the at a distance from this element at a distance of 10 centimeter. You have to find the magnetic field here dB. So you are not supposed to find the magnetic field due to the whole length of the conductor, just due to this element of. So now what we'll do, we'll use according to so this element can be here or it can be here also. 1 mm I can choose here also. 1 mm I can choose here also. The contribution of this. Now we know that from a current element, according to Biot-Savart law, this is the solution. If you have a current element I dl, then from that current element, small element of length dl, just like here 1 mm, at a distance r, at this point, the dV is this is the formula. So therefore, we will put all those values and get the answer. There is nothing you have to understand more, there is nothing more to read in this question. So this ideal element will be in this direction. This is one vector, and this r vector is in this direction. The angle between them is 45 degree. Putting those values, 10 raised to minus 7 here. I is √2. dl is 1 mm, which is 10 raised to minus 3 meter. Sine 45, 1 over √2 r square. What is r square? R is 10 centimeter, that is 10 raised to minus 1 meter. Squaring it, it is 10 raised to minus 2 meter square. You can cancel this goes off. This is 10 minus 2, 8. This is minus 8 is the answer. 8 Tesla. And what is the direction? Direction conductor current is in this direction. So dot from in this side and cross in that side. So it is down, vertically downward. This is the answer to this question. Now let us take one more question. Along a circular coil of 1000 turns. Question number 3. So this is the question, and we'll see the solution. There is a circular coil of n 1000 turns. So n is 1000 is a coil of single turn. So we have got lot many turns, around 1000. Radius of this is 10 centimeter, which is this much meter. This is a number, so no unit. And the current flowing here is I, which is 5 ampere. You are asked to find the magnetic field at the center. So center to dot. by rule it will be pointing off, so it is this. So B at the center is vertically upward. So B, you have to find the magnitude because direction is fixed. If it is anti-clockwise, it is vertically upward. If it is clockwise, then vertically downward. So direction is both way, whichever direction it is flowing. So B is shown to be. You know that at the center of the circular coil, the magnetic field is 2 pi I by R. So if this is for one turn, if you have got n number of turns, so multiply n. So this is the complete picture. Now putting the value 10 raised to minus 7 for this, 2 I pi n, all this value I'll put. Solving this, we'll get the answer. So 10,000 4 minus 3, again minus 2, so 3.144 pi and 10 raised to minus 2 Tesla. This is the answer to this question. Let us take one more question. Question number 4. The electron So this is the question. The electron is moving in hydrogen atom in a circular orbit. So what is the number of orbit? Not given, but as the radius is this, we know that. Okay, that we'll discuss later. And what we have to find is the magnetic field at the center of the circle. So this is basically the same question. Here is a circle. This is the orbit. This is the center. The center is nothing but a nucleus. The electron is suppose moving like this. This is the electron moving. So current will be in this direction. The current will be in the clockwise direction if the electron is moving in the anti-clockwise direction. The flow of the charge in a given time is current. So the current is in clockwise sense. Now, it's not talking about which orbit the electron is. It is seen from here. It is the first orbit. So this orbit is first orbit. That you will know in 12th standard that in the first orbit the radius is 0.53 angstrom. Radius of the first orbit is this. And if you want to find the radius of any other orbit, then it is n square times the first orbit. That you will learn after few months. But anyway, if the orbit is 2, this is 4 times this value. This number is similar to this number because it's 10 raised to minus 10. So we converted it to like that. So, so this is the first orbit in which electron is moving, and whichever orbit it moves, the radius is given to us. We have to find the magnetic field at the center. So if the electron is like this, the current is clockwise, so magnetic field will be downward. If electron is moving anti-clockwise, the current will be clockwise. So magnetic field will be downward because clockwise it will be downward. The magnetic field at the center of a circular coil is given by mu 0.4 pi 2 pi I divided by R. This is for a full circle because this pi 2 pi basically it starts for the angle you consider for a circular coil, this angle is 2 pi. If it is half circle, it is pi. If it is 1/4 of the cycle, that is pi by 2, and so on. So basically, this is theta that we discussed in our theory. Now, in one rotation, so because how many rotations not asked. If it is one rotation, then we will consider 1 coil. Two rotations, 2 coil. So we'll consider one number of turns 1. In one revolution, the n value is 1 for one revolution, and this value is known. 2 pi is known. R is also known. So what is not known is the current that will produce. It's moving with the speed of this 2 into 10 raised to 6. Generally, it is 2.18 or 2.2 10 raised to 6, but it is rounded up to 2 10 raised to 6 meter per second. Now, how to get current from the speed? Now, that I is required. How to find I? Now, I'll just write I for you. The I, here I'll write, the I is the charge that is moving, that is electron. One electron is there in hydrogen atom, divided by the time in one complete rotation. That is the time period of the revolution of the electron. But how to find time? Time is, the velocity is distance upon time, the speed with which it covers. Is distance by time, distance is 2 pi r divided time. So time is distance by speed. Time is distance it covers in one rotation is 2 pi r divided by speed. That is the time. So time is known. So this is what is the current. So you have to substitute the value of current here. If you substitute the value of current as this here, what will get? Mu naught upon 4 pi, 2 pi divided by r, and I is EV divided by 2 pi r. This 2 pi cancels, and rest you have to put the values. Mu naught upon 4 pi 10 raised to minus 7. EV, that is charge of electron, that is 1.6 10 raised to minus 19 coulomb. This means the velocity speed is given to 10 raised to 6 divided by this r and r, that is r square, that is square of this number. Solving this, you will get the answer in Tesla, and I will just write it for you, but I will not solve for you. So this is number, so it comes out to be 11.39 Tesla. You can solve on your own. Okay, this is question number 4. Now let us take one more question, question number 5. Now a straight wire, that is a straight wire, current is 12 ampere, and it is bent into a semicircular arc of radius 2 centimeters. So the question is, I'll just draw the question for you. That is a straight conductor. It is bent into a semicircle of radius r equals to 2 centimeter. So r is 2 centimeter, and the question is, this carries the current of 12 ampere. We are asked to find the first question. What is the magnetic field at O? That means this point is O. Due to straight segments, straight segments, what is the magnetic field? In what way the contribution to B from the semicircle differs from the circular loop? In what way does it resemble? And what will be the answer to circular? Now the first question is, what is the contribution of magnetic field at O due to the straight part of the conductor? You can see that the straight part of the conductor carries the current 12 ampere. If you extend it further, you will get a point O. If I choose any element, here of length dl, that dl length element and the is in this direction, and r also is in this direction. So that means I dl vector and r vector, the angle between them, theta, is 0 degree. in this case also, so here it is 0, and here for this case it is, if I consider an element here, this is your r vector and this is your dl vector. Okay, so in this case theta is pi. In this part of the left part of the conductor, theta is 0. Whether it is pi or 0, if I were to find the magnetic field here from Biot-Savart law, delta V equals to mu 0 upon 4 pi ideal sin theta upon r square. So theta here is 0 or pi in both the cases, straight part of the conductor, 0 for the left part, pi for the right part of the conductor. So this will amount to 0. So the magnetic field due to the straight part of the conductor at the center will be 0, because that is because of the angle which is 0 or pi. If I ask you to find what is the magnetic field at the center due to the circular part, then we can find it is clockwise. The current is clockwise, and therefore it will be into the plane of the paper. So it will be into the paper, and its value will be mu 0 upon 4 pi theta I by r. What is theta here? Theta is the angle the arc length contributes at the center. This is arc length. This contributes this much of angle. This angle I got the theta here. A semicircle contributes an angle of pi. So therefore, for a semicircle, pi I by r. So therefore, 10 is to minus 7, 3.14, I is 12 divided by r, 2 centimeter, that is 2 into 10 is to minus 2 meter. So finally, this will be the, what we solve this and we will get the answer. And the answer comes out to be, okay, I'll just write the answer for you, 1.9, 10 is to minus 4 Tesla. You can check at home that it will be 1.9, 10 is to minus 4 Tesla. Now, if I put this upside down, that means if I put this semicircle not in this side, in other side, then it will be something like that, like this, inverted. If you invert this, then current will be like that. In that case, it will be pointing off. So basically, there is no difference in the magnitude of the magnetic field that you will get if the semicircle lies on this side of the straight part of the conductor or lies on that part of the straight conductor. There is no change in the magnitude, only direction will get reversed. Okay. Thank you.